Do you believe you understand what distance is? Easy. You reach out your hand. Far. Near. 1 meter is 1 meter. 1 mile is 1 mile. You take one step, then another, and you think you're moving through space like walking on a fixed road. Simple. Clear. Obvious. Wrong. Not just slightly wrong, wrong at the level where we've misunderstood the nature of space right from the starting point. And when you truly see what distance really is, when the familiar veil falls away, the entire universe reshapes itself right before your eyes. I'm going to show you. Look around the room you're sitting in. You think you're a few meters away from the wall. You believe the table is over there and you're over here. But your sense of distance doesn't come from the universe. It comes from your feet, from your vision, from living on a small planet where everything happens so slowly and flatly that it tricks you. You say the moon is about 384,400 kilometers from Earth. Sounds solid enough. But that's just one version of the truth, a convenient description. In another frame of reference, that number changes. If you move fast enough, that distance shrinks. If not time curves, distance shifts. If light tells the story, you only get the moon's position in the past. So how reliable is how far away, really? Distance seems foundational, yet it's a sophisticated illusion we cling to in order to feel like we understand the universe. I'm here to peel back each layer, and I promise, once you see what's behind it, you'll never look at space the same way again. Now, before we keep peeling away these layers of illusion, let's talk about something everyone thinks they understand clearly. The light year. It sounds very distant, very far away, right? But actually, a light year isn't a unit of distance at all. It's physics' lazy way of saying that's how long it takes light to crawl from there to here. Light traveling at 299,797,458 meters per second, a number officially fixed in 1983, is the universe's mail carrier. And we're using delivery time to measure distance. So when you say the Andromeda galaxy is 2.5 million light years away, what you're really saying is, I'm looking at something that happened 2.5 million years ago. Not now. Not the current distance. Just the past delivered at very high speed, but still not fast enough to catch up to the present. Imagine looking out your window and seeing car headlights on the street. You think the car is there. But then someone tells you, oh, that car turned from 1990. That's exactly what light does to us over and over, everywhere in the universe. And because light is always one beat behind reality, every measurement based on light is delayed. Like it or not, the real position of galaxies, stars, planets is always hidden behind a subtle fog that light creates. But don't worry, this ambiguity is only the first chapter in the book titled Physics Likes to Mess with Humans. In 1905, Einstein made the whole world uncomfortable by declaring something any sober adult of that time would have considered absurd. Length is not fixed. It sounds like he was taunting the entire scientific community. Oh, your ruler? It's not real. But Einstein wasn't joking, and what he proposed wasn't some vague philosophy. It was a razor-sharp knife straight to the heart of common sense. According to him, it's not objects naturally shrinking. It's space-time, the vast stage on which all motion plays out, forcing you to see things in completely different proportions when you're moving fast. If you accelerate, you step into a new frame of reference, and that frame rearranges the world according to a geometry human senses were never trained to grasp. That's called length contraction, and it's real. Not kinda, sorta true according to equations, true according to equations, true to the point you can't ignore it. At 10% the speed of light, objects ahead of you only shorten by about 0.5%. Hard to notice unless you're the type who carries a micrometer everywhere. But at 90% the speed of light, you suddenly enter a different world. Objects are only 44% of their original length. In other words, if a 10-meter bus is in front of you, to your eyes it's about 4.4 meters. At 99% the speed of light, contraction drops it to 14%. A 1-meter steel rod becomes 14 centimeters. Imagine it. The entire universe becomes a crumpled version of itself. Not because anything is under crushing force. Not because the universe hates you and tries to squash everything. but because you're viewing the world through a ruler twisted by your own motion through space-time. If you race near the speed of light chasing the bus ahead, the bus looks like it's been thrown into a hydraulic press squashed, shortened, but rest assured, the bus doesn't feel pain, doesn't even know you're seeing it distorted. It remains exactly the same in its own frame of reference. You're the one living in a bizarre version of reality where everything is compressed along your direction of motion. And the weirder part? You don't even need to chase a bus to see this effect is real. Muons created in Earth's atmosphere too short-lived to reach the ground under normal lifetime do. Reach the ground because in their frame of reference, the atmosphere has been contracted significantly. That's not theory. That's repeated experimental observation over decades. When you apply this idea to cosmic distances, things get way more interesting. We say the Andromeda galaxy is 2.5 million light years away, but that's only true if you're standing still on Earth. If you accelerate to 99% the speed of light, that distance in your frame shrinks to about 350,000 light years. It's not that Andromeda is rushing toward you like a cosmic whale. It's that space-time has reshaped itself around you. Distance and time aren't independent entities. They're intertwined like two violin strings, and when you change speed, you're plucking a different note that makes both strings vibrate in a new pattern. And if you could accelerate even further close to the speed of light, all distances along your direction of motion keep contracting, getting shorter and shorter, until for a photon, distance appears to become zero. From light's perspective, the entire universe is flat as a sheet of paper. So what do we take away? Something deeply uncomfortable for intuition. Distance isn't something the universe gives you. There's no absolute map, no truly fixed number. Distance is an experience, a viewpoint, a version of reality that depends on how you're moving through space-time. You change speed, the universe changes appearance. What you call far isn't a universal truth. It's just your perception. And you know what's funny? All of this is still just the surface of relativity, but the story of distance doesn't stop at space-time contracting when you move. Einstein wasn't done with his tricks. In 1915, he delivered a second punch to human intuition, general relativity. This time, he didn't just say length changes. He declared that the entire space you think is flat, stable, and well-behaved is actually bent, warped, dented, and bulging constantly by the very matter and energy in the universe. In other words, you're not living in Euclid's neat geometric box where straight lines are shortest. You're living on a giant rubber sheet being pulled, pushed, and squeezed by everything with mass. And distance is no longer the absolute length between 2 points. It's the length of the curve that space-time allows you to travel. Want proof? No need to go to another galaxy. Just look at your phone. The GPS system used by millions every day to find the nearest Starbucks only works accurately, thanks to general relativity corrections. Clocks on GPS satellites run faster than ground clocks by about 38 microseconds per day because time flows differently in weaker gravity at orbit. Without correction, positioning signals would be off by kilometers in just one day. That means in everyday life, you're relying on the fact that space-time curves around Earth. No curve. You get lost. Still, to feel curved space more clearly, leave the ground and fly. Great, you pull up a flight map from New York to Tokyo. On a flat map, the straight line between the cities looks shortest, but planes fly up north along a great circular arc of Earth. Why? Because on a sphere's surface, that curve, not the straight line on the flat map, is the shortest part. That strangeness is a mild taste of non-Euclidean geometry, the kind Einstein baked into the soul of space-time. Now let me take you back to 1919. An international team of scientists led by Arthur Eddington observed a total solar eclipse, testing Einstein's prediction that light would bend when passing near the sun. Result? Stars behind the sun shifted exactly as predicted. Newspapers worldwide exploded. A theory shakes the foundations of physics. For the first time, humans saw with their own eyes that the path of light isn't straight. It's a geodesic in curved space. See? The curvature of space isn't far-fetched. It's why asteroids don't fly straight but fall into orbits. It's why planets orbit the sun not because of some mysterious pull, but because they're following straight lines in curved spacetime. Einstein didn't just change how we calculate, he changed how we imagine the universe. And from here, the concept of distance is no longer a straight line between 2 points. Because straight lines don't even exist, distance becomes the length of the curve spacetime imposes, meaning it depends on geometry, on how mass is distributed, on where you stand. 2 points 1,000 kilometers apart on a flat map might be 1,002 kilometers or 998 kilometers in curved spacetime. And if the universe spans billions of light years, imagine how complex that geometry gets. You can't say how far without asking back. In which geometry? Einstein killed absolute distance, not with philosophy, but with mathematics, experiment, and a cold, sharp look at reality. So if you still believe in Euclidean distance, I'm sorry to inform you, the universe doesn't use our straight rulers. It uses its own shape. If you think curved space-time already makes distance ambiguous enough, congratulations, we've only reached the second layer of this multi-layered cake. Because even when you accept distance changes with velocity and geometry, you still have to face a sneakier truth. In cosmology, there isn't just one kind of distance. Not because physicists love making things more complicated than necessary, but because the universe forces us to think in multiple ways depending on what the distance question is for. Want to know how far between two galaxies right now? That's proper distance. Want to know their distance accounting for cosmic expansion over time? No, that's co-moving distance. Want to know how far light has traveled to reach your eyes? That's light travel distance. Want to measure a galaxy's brightness to calculate distance from light dimming? Welcome to luminosity distance. And the strange thing is, all four concepts, despite different definitions, are completely valid. None is the most real, because space is expanding, light is delayed, and cosmic geometry changes over time. So when you ask, how far away is that galaxy? The most honest answer is, which way do you mean? That's not circular. It's cosmic sincerity. You can find sources listing a specific galaxy as 30 million light years from Earth by light travel distance, but 40 million by current proper distance, and yet another number by co-moving distance to account for expansion. No astronomer messed up. All three numbers are correct, just correct for three different purposes. The universe never promised us a single number. That's our expectation error, not the universe's fault. We grew up with Euclidean geometry so simple it soaks into our bones. 2 points have one unique, unchanging, clear distance. But the universe didn't read our geometry textbooks. When space itself expands over time, when light always tells stories of the past, when matter curves everything around it, then how far can't be a single number. Distance in the universe is a function, a context, a flexible concept depending on what you're measuring. Imagine reading a city map. Walking distance, driving distance, drone flying distance, subway distance, all. Give different numbers and none is wrong. The universe is the same, only billions of times more complex and with far fewer clear lines to cling to. And if you feel a bit disoriented hearing this for the first time, remember, even famous physicists were once shocked to realize distance, the most foundational thing they thought, turned out to be an observer model-dependent quantity. The key is not to force the universe into our mold. It's to learn to ask the right question that fits how the universe actually works. Because when you change the question, the universe changes the answer. And sometimes, just by asking a new question, you've taken one more step into how space-time really operates. So let's dive deeper into the bizarre trick that space-time plays on us, the same trick Einstein revealed in special relativity. But now you're starting to see its full audacity, because length contraction isn't just a pretty formula in textbooks. It's how space-time forces reality to behave according to strange rules that human senses were never designed to understand. And the deep reason is this: the universe demands that the speed of light remain constant no matter what you do. That's not a polite suggestion. It's law, a hard law. A law that everything else, including length and time, must bend to obey. When you accelerate, you can't make light go faster to make sense. Instead, spacetime reshapes itself to ensure the speed of light stays exactly the same. And it does so by compressing lengths along your direction of motion and stretching time in ways you can't feel. In part 3, we saw length contraction through the squashed bus example for a fast-moving observer. But now, let me take you into a truly spectacular example. A natural experiment happening right in front of us every day, yet humanity only grasped its meaning in the mid-20th century. In Earth's atmosphere, when cosmic rays from space slam into air molecules, they create particles called muons. Muons look like electrons, but are about 207 times heavier. They're produced at altitudes of about 10 to 15 kilometers, and they have one extremely important trait. Muons live very briefly, only about 2.2 microseconds in their own frame of reference. With such a short lifetime, even traveling near the speed of light, muons shouldn't reach the ground. They decay midway. Classical calculations confirm that. But in the 1940s, 1950s, physicists were stunned to see swarms of muons still arriving at the surface. Not a few stragglers, thousands, millions. Enough to measure clearly. That was impossible to view through our Euclidean eyes, but completely sensible through Einstein's eyes. Here's the spacetime prank I want you to see clearly. Time slows down for muons moving near the speed of light. They think they only live a few microseconds, but in their frame, that time stretches out much longer. That's half the story. The other half comes from length contraction. From the muon's perspective, the atmosphere is no longer 100 kilometers thick. It's compressed, contracted along their downward path, sometimes reduced to just a few kilometers in their frame. So instead of crossing 100 kilometers, an impossible journey in their lifetime, they only have to cross a much more reasonable, contracted distance. That's how they reach the ground. Not because muons break physics laws, not because they mysteriously live longer, but because distance and time aren't independent. They adjust to keep the speed of light invariant. Muons prove what special relativity was once heavily criticized for. Lengths really do contract when objects move fast. That wasn't in textbooks during Einstein's time. It was right in the atmosphere. Humanity just took decades to understand what it was seeing. And if you want to appreciate the subtlety of length contraction, try looking at the situation from both sides. This is the most fascinating part in the muon's frame. The atmosphere is compressed, the path shorter so they have plenty of time to reach the ground. In Earth's frame, time slows for the muons, making them live longer than normal, enough to cover the 10 to 15 kilometers. Two perspectives, two different stories, but both describing the same single physical event. Neither view is more correct. Both are correct in their own way, and that's the essence of relativity. You never get to declare your observation absolute. When you move fast, you don't just change time, you change distance. Not because the universe likes to trick you, but because it operates on principles far deeper than sluggish human intuition. To see how radical this is, go back to the idea we explored earlier. As you approach the speed of light, the entire universe contracts along your direction of travel. Distant galaxies millions of light years away suddenly become closer in your frame. That doesn't let you go faster than light, but it dramatically alters the geometry of the journey. That's why an imagined astronaut flying to Andromeda in their lifetime doesn't violate laws. They just reshape space-time by moving fast. See? Length contraction isn't a minor detail in relativity. It's a core piece, confirming that distance isn't foundational. It's a consequence of how you move through the fabric of space-time. When you change velocity, you change the world you live in. You're not bending objects. You're bending the story you tell about their positions in the universe. And if all this is starting to make you doubt the ruler you're holding, good, because we're about to reach the part where space itself starts stretching, rippling, and doing things even stranger than length contraction. And if length contraction has already made you see distance as far more fragile than you imagined, then brace yourself. Because now we're stepping into a realm where every notion of how far completely collapses, the world of the photon. Because of the speed of light, the very idea of going from point A to point B no longer means anything. And this isn't abstract philosophy. It's a direct conclusion from the mathematical structure of relativity itself. Let's start with a question that seems simple but is actually extremely dangerous to intuition. How does a photon experience time? The answer, according to Einstein, is it doesn't experience any at all. In the language of relativity, every object has something called proper time, the personal time. That object lives, experiences, feels. It doesn't depend on the observer. It's the object's own clock in space-time. For you, proper time matches the time on your wristwatch. For the muon from earlier, its proper time is about 2.2 microseconds. But for a photon, a particle of light, traveling exactly at the speed of light, proper time is 0. Not close to 0. Not extremely small. Exactly 0. What does that mean? It means that in the perspective of the photon, when we take the equations to their mathematical limit, no time passes, not a trillionth of a second, not a billionth of a second, from the instant the photon is born to the instant it is absorbed. Its entire journey, whether a meter, a light year, or 10 billion light years, happens in exactly one single moment, its own, now. And if you have no time passing, you also have no path. A path only makes sense when you say, I took this much time to travel this much distance. The photon has none of that. For the photon, distance doesn't exist as an experience. From here, we reach an even more shocking conclusion. If proper time equals 0, then the length of the path for the photon is also 0. It's not that the universe suddenly shrinks. It's that in the space-time of the photon itself, the point of emission and the point of absorption coincide. They coincide in the mathematical sense of Minkowski space-time. What you think is a journey across the universe lasting millions of years, for the photon is just a single contact between 2 points. You can picture it like this. To a photon, the entire universe is like a flat sheet of paper right in front of its face. No depth, no distance, no journey. Just a perfectly flat map where every point you call far apart sits right next to each other in the light's frame. This sounds like magic, but it's a direct consequence of the equation. As velocity approaches the speed of light, length along the direction of motion approaches 0, but only the photon actually reaches that velocity. So only the photon gets to enter the state where distance fully collapses. This is why light is such a special tool. It tells us the story of the universe, but it never tells the distance the way we experience it. When a photon leaves the surface of a star, 1 billion light years from Earth, and 1 billion years later, it reaches your eye. You imagine it has traveled a journey so long humanity can't even picture it. But to the photon, the event of emission and the event of hitting your retina are separated by exactly one single point in its experience. You see the path. The photon sees none. You see time. The photon sees none. You think the universe is vast. The photon thinks the universe is flat and has no distance. This is Einstein's third blow to human intuition. And the hardest one? Distance doesn't just change with velocity or geometry. It can vanish completely in some frames. Let that sink in for a moment. From the photon's perspective, every star, galaxy, planet, black hole, gas cloud touches each other. Your three-dimensional universe spanning billions of light years is just an illusion that appears when you live slowly, heavily, trapped in your own proper time. And if you think this shakes the foundations of the concept of distance, you're absolutely right. But trust me, we still haven't reached the deepest layer. Curved space isn't just a beautiful idea in textbooks. It's one of the subtlest tricks the universe plays on our intuition. After getting used to the photon seeing distance as 0, you might think you're immune to every trick. But hold on. Curved space-time will make you realize that even the question, which path is the shortest, isn't simple at all. In the Euclidean geometry you learned in elementary school, a straight line is the shortest path between 2 points. But that's the law of a flat, clean world untouched by matter's curvature. The universe never signed a contract to obey that. Instead, it uses a concept called the geodesic, the shortest curve that light or matter can follow in curved space. That sounds abstract, but imagine you want to fly from New York to Tokyo. You look at a flat map and draw a straight line. But when the plane takes off, it flies north over Alaska. Why? Because Earth is a sphere, so that curved path is actually shorter than the straight line you saw on the flat map. That's the power of curved geometry. It fools you. If you think your map is reality, try wrapping it around a grapefruit. You'll see the world isn't flat like you thought. In cosmic space, things get even stranger. Space is warped by mass and energy, and geodesics aren't determined just by spatial shape, but also by how curvature evolves over time. When light passes near a galaxy or a massive galaxy cluster, its path bends along a geodesics, except light is sliding along the edge of a giant invisible bowl. This isn't theory, it's observed fact. In 1995, the Hubble Space Telescope captured spectacular images of gravitational lensing strange arcs of light around galaxy clusters. They looked like someone held a curved mirror and bent the images of background galaxies into nearly circular rings. But there's no mirror, no transparent object bending the light, just curved spacetime. Light is following the shortest path that cosmic geometry allows, and that path is anything but straight. This leads to a crucial conclusion. In curved space, you can't define the distance between 2 points simply by connecting them with a straight line. Straight lines don't exist anymore. Or rather, they only exist in your head when you draw flat maps. The universe doesn't run on those maps. It runs on its own curved geometry. You can't force onto a sheet of paper without tearing it. If you want the real distance between 2 points, you have to calculate the geodesic length. And that length changes with mass, with energy, with the expansion of the universe, with time. Meaning in cosmology, distance isn't a fixed quantity. It's a complex function, depending on far more things than you want to admit. Let's go back to gravitational lensing for a moment, because it's the clearest example that distance isn't simply how far. You see a galaxy stretched into an arc. Its position looks like it's in one place, but really it's a complex curve of light traveling around a mass cluster. Sometimes light from the same source splits into 2, 3, even 4 different pairs, creating multiple images of the same galaxy. Each path follows a different geodesic. Each geodesic has its own length. Each length depends on the curved geometry of space at the moment the light passed through. So a single galaxy can have multiple different distances depending on which path of light you're looking at. That blows up the idea that distance is unique. Distance in curved space isn't the length between 2 points. It's the length of the path that nature chose to bring information to you. If nature finds 2 paths, you have 2 distances. If 3, you have 3. And all are correct. You can't cram curved space into your flat geometry without causing trouble. If you draw a map of the universe on flat paper without letting it curve as it wants, then it's no longer a map. It's imagination. This is a perspective that shakes our classical thinking. We're used to imagining the universe follows Euclidean rules, points, straight lines, right angles. But Euclidean geometry is the exception, a temporary privilege in regions of space too small and too empty of matter to bend everything. When you scale up to galaxies, clusters, billions of light years, Euclidean geometry dies instantly. In the real universe, straight lines are rare. Curved is normal. And because distance depends on those curved paths, you can't ask how far without following up in which geometry. This is one of the biggest lessons general relativity wants us to understand. Distance isn't an independent property of the universe. Distance is a property of geometry. Geometry is a property of mass and energy. And mass, energy, never stands still. So distance, the thing you thought was foundational, turns out to be a flexible, sensitive, ever-changing quantity, always negotiating with the shape of space-time. That brings us to an even deeper realization. If the geometry of space-time determines distance, then anything that changes geometry changes distance. Even the strange things we'll meet in later parts like entanglement, wormholes, and holography. Curved space is strange enough, but it's still not the wildest version of the universe. Because space doesn't just curve, it moves, ripples, stretches, and actually changes length over time. If you ever thought distance was a fixed number, this is when the universe steps forward and says, sorry, but I'm not the static stage you thought I was. I'm an actor. This isn't philosophical speculation. It's the result of a spectacular discovery in 2015 when LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time in history. Those ripples were predicted by Einstein in 1916, but humanity took nearly a century to hear the breathing of space-time. Gravitational waves aren't waves traveling through space like sound through air. They are vibrations of space-time itself, like dropping a stone into a pond. The water ripples. When two black holes collide billions of light years away, space-time ripples too, and those ripples reach Earth. The terrifying yet beautiful part is, when gravitational waves pass through, distances between everything change. Not metaphorically, literally. If you had two rulers a few meters apart, a gravitational wave could make one longer or shorter without you noticing. LIGO detected gravitational waves by measuring exactly that. Their instrument is an interferometer with two 4-kilometer arms at right angles. When a gravitational wave passes, one arm stretches a tiny bit, the other compresses a tiny bit. And that difference is recorded by laser beams shining along both directions. You think tiny bit means what? Not millimeters, not nanometers. The stretch squeeze change in the arms is about 10 meters smaller than the diameter of a proton, meaning if a proton were the size of Earth, the change LIGO detected would be the diameter of a hydrogen atom sitting on the ground. That's the sensitivity needed to hear the heartbeat of space-time. And when LIGO measured that signal, what it proved very clearly is space isn't a static backdrop for the universe to play out on. Space is part of the universe, and it performs along with everything else. If the distance between 2 points changes just because the gentlest ripple of space-time passes through, then distance can't be an absolute number. It depends on the state of space-time at the exact moment you measure. This even shakes the classic picture of the ruler. You thought the ruler was the absolute standard of length, but the ruler is also an object sitting in space-time, meaning when space-time stretches or squeezes, the ruler stretches or squeezes too. The tool you use to measure distance can compress or expand with the rhythm of the universe. And if both the distance and the measuring tool change, where is the true length? The answer? Nowhere. Length isn't an intrinsic property of objects. It's a relation that depends on the surrounding space-time. You're trying to measure a table with a ruler, but both the table and the ruler are expanding and contracting with the rhythm of something invisible gravitational waves passing through from events billions of light years away. The universe whispers to your ruler, and the ruler answers by shifting a few tenths of a proton's diameter. You don't see it, but physics does. This leads us to one of the deepest truths of general relativity. Space doesn't just curve with matter it oscillates. It is elastic. It responds. It changes continuously. Space has dynamics. Space has behavior. Space is not passive. Space is a dynamic entity. If you could shrink down and stand on the lattice of space-time, you wouldn't see a rigid, flat plane. You'd see a membrane rippling, undulating over time like the surface of a drum still ringing after each strike. Except the strike happens when two 30 solar mass black holes collide, 1.3 billion light years away. And we clumsy, oversized creatures living on a small rocky sphere are perceptive enough to hear that ring. Distance in this context is no longer a fixed quantity. It is alive, changing. A star X light years away today might be X plus thide. Tomorrow, not because it moved, but because the space between us and it has stretched, rippled, reshaped. When the measuring stick doesn't stand still and space doesn't stand still, the only thing left is to accept distance isn't a property of 2 points. It's a temporary property of space-time at the moment of measurement. That's why every notion of cosmic distance must be calculated in dynamic geometry, not static geometry. And that's why we're moving farther and farther away from what Euclid ever taught. Entanglement is where the concept of distance finally collapses completely, and where Einstein, the man who once upended classical physics, suddenly becomes the most uncomfortable person in the room. After getting used to curved space, stretching rulers, slowing time, and photons that don't travel from anywhere to anywhere, you might think you're ready for surprises. But entanglement doesn't care if you're ready. It walks in and smashes the last scraps of intuition about near and far. The story begins in 1935 when Einstein, Podolsky, and Rosen published their famous paper describing what became known as the EPR paradox. They wanted to prove that quantum mechanics, which was developing furiously at the time, could not be the complete picture of reality. The reason was simple. It claimed two particles could be linked in such a way that measuring one instantly determined the state of the other, no matter how far apart they were. Imagine creating two particles, letting them interact until they become entangled, then sending one to Los Angeles and the other to New York. Quantum mechanics says if you measure the particle in New York, you instantly know the result for the one in Los Angeles. Einstein hated this. He called it spooky action at a distance, a ghostly behavior that completely contradicted the principle he had built. No information can travel faster than light. Einstein thought there must be something hidden inside, some hidden variables deciding the measurement outcomes in advance. Quantum theory is just missing data. But in 1964, John Bell showed something that shattered that hope. If hidden variables existed, measurement outcomes would have to obey a certain mathematical limit called Bell's inequality. All it takes is one experiment violating that limit to know the universe doesn't have the kind of hidden variables Einstein wanted. Math alone wasn't enough, proof was needed. That's when Alan Aspect stepped in. In 1982, in a series of bold experiments, Aspect tested Bell's inequality using entangled photons. The result, Bell's inequality was completely violated, meaning no hidden variables, no secret signals faster than light, and no classical mechanism could explain the link between the two particles. It was as if the universe stood up and declared, Einstein, your idea was beautiful, but reality doesn't work that way. This leads to an astonishing consequence. Distance means nothing to entangled particles. Whether two particles are a meter apart, a kilometer apart, or a billion light years apart, the connection behaves as if they are sitting right next to each other. Imagine putting two coins in two envelopes, sending one to Brooklyn and the other to Manhattan. You open one and see heads. The person opening the other sees tails instantly. No phone, no radio waves, no miracle. But entanglement is stranger than classical coins. With real coins, you could say the outcome was predetermined. With quantum particles, you can't say that. If you change how you measure the first particle, for example, tilting the measuring device in a different direction, the outcome for the second particle changes accordingly in an exact correlation, even though you never touched it. No mechanism transmits information. No signal pulse races through space. No violation of the speed of light. Just the fact that space does not separate these two particles. And that's what Einstein could not accept. He believed in a local universe, things far apart or independent. But entanglement shows locality is just an illusion, a habit of thought born from our slow macroscopic world. At the quantum level, far has no meaning. Two entangled particles are not separated by space. Space is merely the backdrop we use to describe classical positions. Imagine the universe as a book, and two entangled particles as two sentences on the same page. You can tear the page and take the pieces far away, but the content remains linked. The information doesn't travel between the sentences because they were written together. Entanglement forces us to admit the hardest thing to swallow. Distance is not a fundamental concept. It does not appear in quantum mechanics the way position appears in classical mechanics. Space is not the foundation of quantum correlations. Quantum correlations are the foundation of how we construct space. And if this sounds like the universe is playing tricks, it is. But just like every physics shock before it, entanglement doesn't come to destroy understanding. It comes to prepare us for a bigger truth. Perhaps entanglement itself is what structures space, rather than space containing entanglement. Two entangled particles don't just make Einstein uncomfortable. They make the entire notion of near and far that humanity has relied on for thousands of years arbitrary to the point of being ridiculous. After EPR and the Bell inequality tests, quantum physics makes a bold claim. Spatial distance, the distance you measure with a ruler, a map, GPS, is not the most important distance. What truly determines the closeness of two quantum systems is the degree of entanglement, which we can poetically call quantum distance. The issue here is, quantum distance has no obligation to respect classical distance. Two particles, thousands of kilometers apart, can be closer than two particles standing right next to each other, but completely unentangled. That's not a metaphorical comparison. That's an accurate mathematical description in quantum theory. You can place two particles a few millimeters apart, but quantum mechanically independent, each living in its own separate world. But you can also create two entangled photons. Send one to one side of Earth and the other to the opposite side, and they still behave as two parts of the same system. The far number on a geographic map means nothing to the quantum world. One of the most beautiful demonstrations of this came in 2017 with China's MICEUS satellite experiment. They created entangled photon pairs on the ground, sent one photon up to a satellite at 500 kilometers altitude, then relayed it to two receiving stations separated by a total of more than 1,200 kilometers. The astonishing result, the degree of entanglement remained intact. It did not degrade with distance. It did not weaken as the photon passed through the atmosphere, the ionosphere, hundreds of kilometers of space. Your classical world would say that far apart the connection has to break. But the quantum world replies, the distance you're talking about has nothing to do with me. Indeed, entanglement does not propagate through space. It is not a signal. It is not a string connecting two particles. It is a global state in which the two particles are described by a single shared wave function. No matter where they are located, you can move one particle to the North Pole or drop it in Florida, and that shared state remains unchanged. This brings us to a crucial question. If entanglement does not diminish with distance, then what meaning does distance have for the connectedness of two particles? If we answer bluntly in the language of quantum mechanics, none. It has no meaning at all. You can put two best friends at opposite ends of the United States, and they remain as close as ever. The two strangers sitting next to each other on a subway have no connection at all. The quantum universe operates exactly like that. Here, quantum closeness means the two systems share a lot of information. They are described by the same total wave function. Quantum farness means they're independent, sharing no information. A photon in Beijing and a photon in Beijing and a photon in Vienna can be right next to each other, quantum mechanically. Two electrons a few microns apart in the lab can be infinitely far if they are not entangled. Our intuition, built in the macroscopic world where gravity, light, and three-dimensional space shape every experience, hates this. But physics has no obligation to make you comfortable. The mathematics of entanglement forces you to accept that classical space is only the topmost layer of a deeper structure, where quantum relations are what define the fundamental fabric of the universe. The MICEUS experiment is just a modern and spectacular proof, but the core idea has been sitting in the equations for nearly a century. Classical distance does not determine the deepest physical connection between two particles. Once the notion of near-far at the quantum level has been completely overturned, we arrive at one of the most radical turning points in modern physics, an idea that, the first time you hear it, might make you think physicists have had too much coffee. The three-dimensional space you live in may not be fundamental. It may only be a projection of a two-dimensional theory lying on the boundary of the universe. That is the spirit of holography. And the historical turning point for this idea came in 1997 when physicist Juan Maldacena published his famous equivalence between two completely different theories. One gravitational theory living in three spatial dimensions plus time, and one non-gravitational quantum theory living in two spatial dimensions plus time on the boundary. The name physicists gave to this equivalence is the ASS-CFT correspondence, and it caused such a shock that thousands of research papers since have tried to extend, deepen, or test it from every angle. What is extraordinary is not just that the two theories look completely different. One has gravity, the other doesn't. One lives in 3D space, the other is flat 2D, but that they describe exactly the same universe. Every phenomenon in the 3D space, including distance, curvature, motion, geometry, can be encoded in the language of the 2D theory on the boundary. In other words, depth may not be something that truly exists. It is emergent, appearing when you describe the world at macroscopic scales. Imagine this with a much simpler example, animation. When you watch a character run into the depth of a scene, you perceive that depth as real, but in reality your screen is just a flat 2D surface. Depth isn't real. It's encoded by size, blur, color, perspective, all two-dimensional information. Or take another example, those 3D illusion posters you see in stores. You look at it and your brain tells you there is depth, but the paper remains flat as ever. Depth is just an effect created from sophisticated two-dimensional encoding. That's exactly what 8S/CFT is saying, except it applies to the entire universe, not just a poster. In holography, points deep in 3D space are not really located somewhere. They correspond to energy scales in the 2D theory. Regions near the boundary correspond to high energy. Regions deep in the bulk correspond to low energy. Depth, the thing you think is real distance, turns out to be just the way we organize quantum information by energy level. 3D space emerges from 2D in a way very similar to how depth emerges from a flat painting. This gives rise to an even bolder claim. Distance in 3D space is actually not a fundamental quantity of the universe. It is merely the result of the entanglement structure in the 2D theory. If two regions on the 2D boundary are strongly entangled, they will be close in the emergent 3D bulk. If the entanglement is weak, the distance in the bulk is large. Thus, what we call far in the 3D world is just a geometric representation of two chunks of information sharing little entanglement. To picture it more clearly, imagine you have a 2D sheet encoding the information of a 3D scene. If you change the degree of information linkage between two regions similar to adjusting interdependent pixels in a compressed image, you correspondingly change the distance between 2 points in the 3D space. In other words, by stretching or shrinking the entanglement structure on the boundary, you are warping space in the bulk in action. That sounds like science fiction, but is a direct mathematical consequence of holography. This is when we realize holography doesn't just say the universe might be like a projection. It says that three-dimensional space may have no substance beyond sophisticatedly organized two-dimensional quantum information, and far near in space is just an intuitive tool we use to understand a far more abstract structure. In this context, distance is no longer the length between 2 points. Distance is the quantum correlation between two regions of the system. Looking from here, the strange features of entanglement we saw earlier start to make sense. Why do two entangled particles behave as if they are next to each other, even though separated by 1,200 kilometers? Because in the language of holography, their degree of entanglement defines quantum distance. And that distance has no reason to match classical distance in the emergent 3D space. In a projection, 2 points on a 2D image may be at opposite corners of the screen, but the encoded content can make them close in the virtual space the image simulates. This leads to an even deeper conclusion. If 3D space is only emergent, then distance can never be foundational. Distance is only a property that appears after the universe has chosen how to organize its entanglement. The universe doesn't come with depth ready-made. Depth is an effect. Space is not a pre-existing coordinate grid. Space is a product. You can imagine Einstein's reaction if he witnessed holography. The man who fought against entanglement would probably be stunned into silence for a few seconds, because holography takes what Einstein considered the most absurd thing, entanglement, and places it as the foundation for building space itself. If holography has revealed that 3D space is only a projection of a deeper quantum structure, then the next step, and also the most spectacular intellectual twist, comes from the 2010 work of physicist Mark van Ramsdonk, who laid the groundwork for a shocking idea. The geometry of space-time itself is a product of entanglement. Distance is merely the way our brains interpret the underlying entanglement structure, not a metaphor, not vague philosophy. It's a mathematical conclusion. Imagine you have a gigantic quantum system living on a 2D boundary, as in the holography picture. Its components are linked by entanglement, forming an invisible but extremely rich network. Van Ramsdonk showed that if you reduce the entanglement between two regions of this quantum system, then in the emergent 3D bulk, those two spatial regions move farther apart. And if you keep reducing entanglement further and further between those two regions, the distance in the bulk keeps increasing. Light travel time increases. The geodesic connecting them lengthens until entanglement reaches zero. And what happens when that entanglement is zero? The emergent 3D bulk splits in two. Two regions of space that were once smoothly connected in your world suddenly become two disconnected fragments of the universe, with no geometric connection left between them. Not because you stretched space with some pulling force, but because space itself has been torn away from its quantum foundation. This leads to a terrifying yet beautiful statement. Entanglement is not inside space. Space is inside entanglement. Space is not a carpet you spread out and then place particles on. Space is woven from the threads of entanglement between particles. Picture a rug woven from thousands of intertwined threads. If you cut away those threads, the rug starts to thin, tear, and eventually splits into two pieces. That's exactly the image Van Ramsdonk describes, except the threads here are not matter, but entanglement, entropy, a quantity that describes the degree of quantum linkage between regions of the system, and the rug is space-time itself. When entanglement is strong, space-time is smooth and continuous. You can travel from point A to point B along a finite geodesic. When entanglement is weak, space-time becomes thin, distorted, distances increase. When entanglement disappears, space-time rips apart. This completely changes how we think about distance. In the classical world, you see 2 points far apart and think, they're far because there's a lot of space in between. But in the quantum picture, distance appears because the entanglement between two regions is low. If you increase entanglement, they become closer in the bulk. Distance is not static. It is the geometric manifestation of a deeper language. And that language is entanglement. Poetically, distance is spacetime's feeling of how much quantum information two regions share. If they share a lot, spacetime contracts, pulling the points closer. If they share little, spacetime expands, pushing them apart. That's why Van Ramsdonk argues that the entire geometry of the universe curvature, lengths, distances, even topological connectivity can be described by entanglement, entropy. You might think this sounds like physics poetry, but the mathematics behind it is rigorous. Physicists have shown that curved spacetime models, even resembling parts of our universe, emerge naturally when you configure the right amount of entanglement on the 2D boundary. And amazingly, you don't need to put geometry into the equations. Geometry emerges on its own. Pause for a second to feel this. Spacetime is not foundational. Spacetime emerges from the web of entanglement. In this world, near and far are no longer absolute measures, but the final expression of a deeper relation, the extent to which two quantum regions hold hands in the system's shared dance. When two regions are strongly entangled, we say they are close, even if classical coordinates say they are far apart. When two regions have nothing to do with each other, we say they are far, even if they sit next to each other in classical space. This strangely fits with everything we've seen in previous parts. Muons live longer because of time dilation, a geometric effect. Photons travel zero distance, a geometric effect. Gravitational lensing bends light paths, a geometric effect. But here the geometry itself is the product of something deeper, entanglement. So if you ask, what is distance really? The modern physics answer is, distance is just the way you perceive the entanglement structure of the universe. The space you're sitting in, the room, Earth, the solar system, the galaxies is all just a rough surface that entanglement weaves from below. So can these deep quantum connections look like geometric connections in the bulk? In 2013, two physicists, Juan Maldacena and Leonard Susskind, answered together, yes. And they are the same thing. They proposed something called ER-EPR, short for Einstein-Rosen bridge equals Einstein-Podolsky-Rosen entanglement, claiming that every pair of entangled particles is connected by a microscopic wormhole, and conversely, every wormhole, even as a mathematical model, corresponds to some form of entanglement. This is not a science fiction claim where you step into a wormhole and pop out on the other side of the galaxy. Wormholes in ER equals EPR are non-traversable, carry no signal, allow no superluminal travel, but they are an emergent geometric structure born from the shared quantum state of two systems. In other words, entanglement is not just a relation between particles. It can be described by a geometric bridge in the Boca bridge that Einstein himself described in 1935 when talking about wormholes, but never imagined would be connected to the EPR phenomenon he himself introduced that same year. The graceful irony of history is this: Einstein accidentally created two separate concepts, wormhole and entanglement, and 80 years later, Maldacena and Susskind came back and said, Einstein, those two things are actually twins. To understand this intuitively, imagine you have two entangled particles. In the lab, they might be a meter, a kilometer, or as in the Myceus satellite experiment, 1,200 kilometers apart. In the classical description, you say these two particles are far apart. But in the ER equals EPR picture, classical distance completely fails to capture the underlying quantum event. Particle A and particle B are not two isolated points. They are the two ends of an emergent geometric structure. That wormhole is extremely tiny, impossible to enter, but it is a real link in the bulk description. Classical space is just the shadow of the deeper quantum structure, and the wormhole is how that structure encodes the connection. Imagine you have two doors in two different cities, but beneath the ground there is a secret tunnel connecting those two doors. You can't use the tunnel to travel, but it still exists and explains why these two doors can influence each other in a special way. The interesting part is that wormholes in ER equals EPR do not break the speed of light rule. They only describe correlation, not information transfer. You can't send a signal through the wormhole, but the wormhole is how emergent geometry records the quantum linkage between the two particles. And here's the key. Strong entanglement, short wormhole, the two systems are close in the quantum sense. Weak entanglement, non-wormhole, the two systems are far in the bulk. Zero entanglement, wormhole disappears, the two regions completely separate. This fits perfectly with Van Ramsdonk's conclusion that reducing entanglement stretches spacetime, and eliminating entanglement tears spacetime apart into two pieces. ER equals EPR just takes one extra step. It says the wormhole is the geometrization of that process. Now look back at entanglement in the lab. Two entangled photons, 1,200 kilometers apart, but still intimately linked. Why? Because in the emergent space of ER equals EPR, they are not far apart at all. They are connected by a quantum geometric structure. If you change the measurement state at one end of the wormhole, the mathematical description of the wormhole knows it and adjusts to preserve the quantum correlations. No signal is transmitted. It's just how the universe preserves its own structure. Classical distance cannot explain this, but emergent wormholes can. This leads to a radical reversal in thinking. Distance is not a foundational quantity describing the separation of objects. It is only the way we interpret the emergent geometry of entanglement. Two particles can be far apart in Euclidean space, but close in quantum space if a wormhole connects them. Two particles can be right next to each other in the lab, but far in quantum space if there is no entanglement. You're using the wrong map. Classical space is just a compressed version of the quantum universe. You look at the compressed map and think some paths are long, some short, but the real structure underneath is what decides what is near and what is far. Now let's apply this to black holes, the objects Einstein built to describe extreme gravity. In holography and ER equals EPR, a black hole is not just a gravitational object. It is a dense network of entanglement. And if you place two black holes far apart but configure their quantum states to be linked, you can have a wormhole connecting them, not for travel, but to describe the entanglement structure of the entire system. This even leads to traversable wormhole models when you add quantum teleportation, but that's a story for later. The key point of ER equals EPR is classical distance does not correctly describe the true level of connection in the universe. It only describes how human eyes interpret emergent geometry. The more accurate, more fundamental, more beautiful description is entanglement. When two regions are strongly entangled, they are next to each other in the deep sense of quantum spacetime. When entanglement is lost, the true spacetime structure tears, the wormhole vanishes, and distance becomes infinite in the geometric sense. In that context, when you ask, how far apart are these two particles? The universe, if it could answer, would say, you're asking the wrong question. The right question is, how entangled are they? When entanglement disappears, space itself disappears. This sounds like cheap science fiction, but it is a mathematical conclusion drawn directly from holographic models and from the arguments of Van Ramsdonk, Maldacena, Susskind, and many other physicists. If entanglement is the threads weaving the structure of space-time, then stretching those threads causes space to expand, and cutting those threads causes space to separate. Picture a simple thought experiment. You have a large quantum system corresponding to the entire boundary of space-time in a holographic model. Between two regions A and B, there is a certain level of entanglement. At high entanglement, the corresponding regions in the bulk are closed, meaning there is a finite geodesic connecting them, and light can travel from A to B in a finite time. If you reduce the entanglement between A and B, the geodesic becomes longer. In geometric language, space stretches, like gently pulling on a sheet of rubber and drawing 2 points farther apart. Distance is not something predefined. It is space-time's response to the underlying amount of entanglement. Reduce entanglement further, and distance increases again. You keep reducing, and then something strange happens. The geodesic connecting A and B becomes infinitely long. That means in the emergent bulk, A and B no longer lie within the same space, not very far, not at the edge of the universe, but in two completely separate spacetimes with no connecting path whatsoever. The universe is no longer connected. It fractures into two pieces. The strange part is that the entire process happens without any physical force, pushing, pulling, or distorting space. You don't need colossal energy. You only need to change, often very gently, the degree of quantum linkage between the two regions. This is the most beautiful aspect of the new picture of space-time. Space is not something that just exists, not an empty container waiting for matter to occupy it. Space is the result of entanglement. And when entanglement vanishes, nothing holds space-time together anymore. It tears. Just like a rug woven from threads, if you cut the threads along the line, the rug doesn't shrink. It splits. In holographic physics, space-time behaves exactly the same way. To see how radical this is, think about distance. In the classical world, distance is simply how far between 2 points. But in the emergent picture, distance is the strength of quantum linkage. Strong entanglement means small distance. Weak entanglement means large distance. Zero entanglement means distance becomes infinite in the geometric sense. You can wait forever and never cross it. Shoot the most powerful laser and still never connect. Space is no longer a static object. It is a byproduct of the degree of quantum coherence between parts of the system. Now ask the question, what makes two regions of the universe belong to the same space? Not coordinates, not positions on a classical map, but a sufficient level of entanglement to keep them within one continuous bulk. Conversely, what makes two regions no longer in the same universe? Not because they drifted apart, but because entanglement dropped to the point where emergent geometry can no longer bridge them. This explains profoundly why entanglement is the central phenomenon in every theory attempting to unify quantum mechanics and gravity. Not just because it's weird, not just because Einstein hated it, but because it is what creates space. If you take a gigantic quantum system and mathematically split it in two, Each half will have its own separate space-time, completely unrelated to the other. Loss of entanglement equals loss of spatial connection. And when we say infinite distance, we are not speaking metaphorically. We mean that in the emergent geometric description, there is no path from A to B. No light can travel. No geodesic exists. Infinite distance means space-time is no longer shared. If entanglement is the glue of the universe, then distance is just the way that glue is distributed. Run out of glue, the universe cracks. This runs completely counter to our classical intuition, where space is seen as a fixed backdrop that cannot be destroyed. But in the quantum picture, space can tear in the strict mathematical sense when entanglement disappears, and we immediately understand that our space depends entirely on entanglement. Then every distance you measure from millimeters to billions of light years is merely a macroscopic manifestation of a complex entanglement network underneath. In other words, distance has no independent substance. If entanglement changes, distance changes. If entanglement vanishes, distance loses meaning. Space exists only when quantum information between parts of the universe remains linked enough to weave them into the same geometric fabric. Luke, quantum gravity takes us into a world where space is no longer a smooth fabric. You can divide infinitely, but a discrete, grainy structure, much like matter, is made of atoms. This goes even further than the idea of space-time emerging from entanglement. It says that space itself has smallest indivisible units. You cannot divide further, cannot measure smaller, cannot define distance in the familiar way. Two physicists, Carlo Rapelli and Lee Smolin, laid the foundations for this theory. According to them, space is not the continuous field Einstein described in general relativity, but a quantum network called a spin network, a lattice of nodes representing quantum volumes, and links representing quantum areas between spatial regions. Each node is an unimaginably small unit of volume. Each link a unit of area, and the entire space you live in is built from trillions upon trillions of such nodes and links. In this description, space is like a digital photograph. Zoom in far enough and you see pixels. You cannot see those pixels at human scales, just as you cannot see atoms in matter with the naked eye. But at the Planck scale, the smallest scale, physics allows you to realize space is not continuous. It is discrete. It jumps in steps. It has structure. And this leads to one of the strangest conclusions in all of science. Below the Planck length, the question, how far, no longer has meaning. The Planck length, about 1.616 tens 10 is so small that if an electron were the size of Earth, the Planck length would be like a speck of dust compared to the planet. No ruler can measure it. No microscope can peer into it. And most importantly, no physical meaning exists below that length. 2 points in space cannot be 10 apart, because space has no grid cell that small. It is not an infinitely high-resolution Euclidean grid. It is a specific quantum lattice. Spin networks are diagrams describing how space is constructed. Nodes correspond to quantum volumes, space grains. Links correspond to quantum areas, dividing surfaces between volumes. These nodes and links change, oscillate, reconnect over time, and those transformations create geometry. Much like vibrating strings produce sound. Space does not exist first and then contain matter. Space is a state of the quantum gravitational field. Distance, in this description, is not a measurement between 2 points on a continuous background. It is the number of nodes, the number of steps in the spin network between two regions. If there are no nodes between two regions, they are in contact. If there are many nodes, they are far apart. And if you want to ask, are 2 points 10 odd apart? The answer is no, because there are no points between them to define such a distance. Earlier we saw in relativity that distance depends on velocity and geometry. In holography, distance emerges from entanglement. But Luke quantum gravity goes further. Distance does not exist at every scale. It only appears at macroscopic scales, where spin networks are so densely packed that human perception cannot distinguish the grains. At the tiniest scales, space becomes a quantum foam of discrete jumps. You're trying to ask the distance between 2 points on a wool sweater, but when you zoom in, you realize the sweater is woven from threads. Distance, smaller than the thickness of a thread, has no meaning. Imagine standing in a room. To you, space is smooth, flat, continuous. But if you shrink smaller than a proton, smaller than an electron, smaller than a quark, down near the Planck length, you would see space no longer flat like a tabletop, but grainy, structured like a graph, with vibrating nodes and quantum jumping links. At that point, the question, how far is the wall from me, no longer has a single answer. Distance becomes discrete, not 3.5 meters, but about 10 scrat nodes. This also explains why space in general relativity can curve. When spin networks reconnect, the number of nodes and the distribution of links change, and emergent geometry changes accordingly. Curvature is not bending a flat plane. Curvature is changing the lattice structure. Loop quantum gravity also resolves one of physics' biggest problems, the singularity. In relativity, at the center of a black hole, density infinite, curvature infinite, distance meaningless. But in LQG, there are no infinities. Only a dense quantum lattice where volume units cannot be smaller than a spin network node. Singularities are no longer physical points. They are merely incorrect descriptions when we use continuous tools to interpret a discrete reality. All of this leads to a powerful conclusion. Distance is not foundational, not absolute, not continuous. It is only the consequence of so many nodes linking into a network large enough to look like smooth space. Cut the network, and space tears. Change how nodes connect, and space curves. Go down to the Planck scale, and space vanishes like mist when you get close enough. If loop quantum gravity shows us that space is built from discrete grains, then the next logical step in thinking is almost unavoidable. Distance is not a fundamental property of the universe, but a statistical illusion, much like temperature. None of us has ever touched the temperature of a single molecule, because it doesn't exist at that level. Temperature only appears when you have trillions upon trillions of molecules colliding, exchanging momentum. And what you call 30 degrees Celsius is not a property of any individual molecule, but a statistical average of them. Distance is the same. It has no meaning at the Planck scale, where spin networks and entanglement are the primitive structures. It only has meaning when you look at the world on enormous scales. The human scale, where every quantum fluctuation, every microscopic linkage, every discrete spin jump is smoothed out by the sheer vastness of numbers. We live in an averaged version of quantum reality, and our brains, which evolved to throw stones, build fires, and run from predators, choose to describe reality with simple concepts like, this is near, that is far, point A is 5 meters from point B. But those numbers are merely convenient ways for us to organize the world at scales our senses can perceive. At deeper levels, where entanglement builds geometry, where emergent wormholes connect points, where spin networks vibrate to create area and volume, there is no distance in the everyday sense. No straight lines, no how far, no between 2 points. All of those appear only when you look at the gigantic collection of nodes, links, and quantum correlations on macroscopic scales, just as temperature appears from the chaos of molecular motion. You cannot ask a single molecule how hot it is today. That question is not meant for it. Just as you cannot ask a node in a spin network how far 2 points are, that question is only for large creatures like us. We are too big compared to the quantum world, so we only see its faint shadow, an averaged, simplified, smooth version. Einstein said space curves, but that was just a beautiful way of saying how entanglement is distributed. Maldacena, a 3D space emerges from a 2D system, but that was just another way of saying distance is created by quantum information. Rovelli says space is discrete, but when you zoom out, that discreteness blurs and looks continuous. All these pictures say the same thing. Distance is a byproduct of statistics. It is the result of averaging trillions upon trillions of quantum linkages that human eyes never see. If you lived at the Planck scale, you would never invent the concept of distance. Space would not be flat, not curved, but a shimmering lattice of jumping quantum connections. Distance only makes sense when you are far enough away that all microscopic vibrations blur, and you see only a smooth, uniform picture, just like temperature. Just as we use temperature to avoid tracking 10 squared R molecular motions in a glass of water, we use distance to avoid describing trillions upon trillions of entanglement fluctuations. Spin network changes in spacetime vibrations. It is convenient, but not foundational. It is effective, but not basic. It is true in our world, but not true at the root level of the universe. And the interesting part is, when you step into the world where distance is emergent, you realize that everything you once thought simple is far more complex. And everything you thought too complex turns out to be surprisingly simple. The deep layer of the universe does not speak the language of distance. It speaks the language of information. Entanglement is the syntax. Spin networks are the vocabulary. And distance, the thing you thought was foundational, is only a story constructed by averaging trillions upon trillions of quantum data fragments. We live inside that illusion, and it is a beautiful, useful illusion. So much so that no one wants to give it up. But to understand how the universe really operates, we must accept that distance is not the original truth. It is merely a convenient habit of creatures too large to see the real structure. Looking at everything we've discussed so far, an almost obvious conclusion emerges. The universe isn't truly vast. It's our senses and our size that make it appear vast. We are too slow, too large, too blind to the quantum layers of structure to realize that what we call cosmic distance is merely a side effect of living at macroscopic scales, where all microscopic phenomena are smoothed out, averaged, and hidden behind numbers like millions of light years or billions of light years that sound profoundly fixed and insurmountable. But that's our problem, not the universe's. From the perspective of a photon, which experiences no time and therefore no length, a journey of billions of light years is just a single contact between two events. In its frame, the entire space between the farthest star and your pupil does not exist. Not very small, not greatly contracted, but zero. The universe isn't wide. We just view it through eyes programmed to interpret reality in the style of ancient savanna-running creatures. For the photon, like leaving a distant galaxy and reaching you is not a trip, it's a single event. Distance, in that frame, is merely a human habit. Even at the quantum level, things become more radical. If entanglement truly weaves space, then distance is just the way the human brain interprets that degree of quantum linkage. Two particles, 1,200 kilometers apart, still behave as if standing next to each other. A particle in New York can be quantumly closer than one placed right beside it, but unentangled. The quantum world doesn't look at the universe through our maps. It looks through networks of correlation. And in that network, far or near isn't the right physical question. It's like asking a single water molecule, is it hot today? The question only makes sense when you're large and slow enough for temperature to emerge. We forget that all our measurements are bound by the speed of light. We look at Andromeda and think it's there, 2.5 million light years away. But we don't see its real position. We see only its past. The distance we assign to galaxies is defined by a creature with slow senses, slow tools, slow life rhythms. If we lived as fast as a muon, near the speed of light, space would contract into completely different versions. Andromeda would no longer be millions of light years away. It would be a few 100,000. Change your frame of motion, and distance changes. Change the geometry, and distance changes. Change the entanglement, and distance changes. Zoom below the Planck length, and distance disappears. Yet we stubbornly say, the universe is so vast. The universe isn't far. We're just clumsy at perceiving it. Because truly, what we call far exists only within the experiential range of a species that crawls at turtle speed compared to light, whose brains lack modules for detecting entanglement. Trapped in a classical world where distance looks solid and reliable. But when we shift perspective to the photon, to entanglement, to spin networks, the universe shrinks, collapses, contracts, until far becomes a concept with no application. Try looking at a star 10,000 light years away. Humans look and think unimaginably far. But in the quantum world, 10,000 light years isn't a barrier. It's delayed information. If the photon carrying the news from there to you experiences no time, then the far you feel is merely perceptual error. If space emerges from entanglement, that far is just a geometric version your system constructs to make it easier to understand. If at the Planck scale there is no distance, that far only appears when you average trillions upon trillions of nodes in a spin network. In short, the distance you perceive is not a fundamental truth of the universe. It's an affliction of macroscopic creatures that need smooth concepts to survive and interpret the world. Our brains flatten, simplify, average to create a universe that is far and wide, while the quantum essence is not wide at all. It is densely connected by entanglement. It has no distance for photons. It has no length below the Planck scale. It has no static geometry, but a vibrating lattice. And it is not a gigantic spatial region. Instead, it is a vast network of quantum information where far and near are only shallow descriptions invented by slow creatures like us to grasp something infinitely more complex. The universe isn't vast. We just look at it with eyes that are too crude. When you look up at the night sky and see the Milky Way stretched like a silver mist across the dark, you feel as though you're gazing into a colossal structure reaching hundreds of thousands of light years. Light from one side of the galaxy takes about 100,000 years to reach the other, and when it hits your eye, you believe you're looking at something far away, immense, beyond imagination. But as we've seen, that's the view of a slow-living creature with slow vision and classical distance thinking. The deeper reality is entirely different. When you look up at the night sky, you're not looking far. You're looking late. You're looking at old photographs delivered at the speed of light, a speed that, for the photon, isn't motion but merely connection. A star 500 light years away isn't 500 light years distant. You're just seeing its 500-year-old self. Its real position isn't where you see it. The way you perceive the night sky is the classical version of a blurred, time-stretched map, not the true shape of the universe. When you look at a galaxy millions of light years away, you're looking at its past, when Earth had neither humans nor grass. You don't see where that galaxy is. You see only where its light once started, reconstructed in a classical frame along a path the photon itself never experienced. But the most important and most fascinating thing is this. When you look up at the night sky, you're seeing traces of entanglement and quantum connectivity, not distance. The stars you see exist in a dense quantum information network, where the degree of entanglement between regions of the universe determines the shape of the spacetime you're experiencing. But the human brain doesn't see that network. It sees only the classical crust of emergent geometry, where bright points look impossibly far apart. You look at a star cluster in the Milky Way and think, these things are next to each other in space. But more accurately, they are points in a vast architecture of entanglement. Architecture of quantum connectivity and classical distance is just a crude projection of that structure. Some regions you see as far away may actually be closer in the quantum sense. Some regions you see as right next to each other may be nearly unrelated at the microscopic level. You don't see the universe as it truly operates underneath. You see a slow, blurred, aged version, distorted by time, a classical picture built from ancient light trudging to your eyes. Imagine looking at a gigantic 1900 traffic map of New York. The roads, buildings, bridges, all outdated, changed, no longer matching the present. You're not seeing New York. You're seeing New York of a different era. The night sky is the same. It's a delayed map, not a positional map. It tells you the story of photons, not the story of space. It tells you a classical past, not a quantum present. You think you're looking at stars thousands of light years away? No, you're looking at quantum architecture filtered through the brain of a slow-living animal. You're looking at a cartoon version of the real universe. When we say the universe is vast, we're talking about our feeling, not the actual structure of space-time. In the photon's frame, Every star you see is right here because the photon has no distance. In the entanglement frame, every point you see is a node in a correlation network. In the spin network frame, every bright point is a result of discrete vibrations with no continuum, no how far. Only humans, living at such mismatched scales, think the night sky is a picture of distance, but in reality it's a picture of information. So the next time you look up at the sky, remember, you're not looking at a vast universe. You're looking at the classical makeup your senses have painted over an infinitely deeper quantum network. You're looking at the history of light, not the positions of stars. You're seeing entanglement architecture blurred by time, not the true structure of the universe. In other words, when you look up at the night sky, you're looking at entanglement and your brain calls it distance. If everything we call distance is just a crude manifestation of entanglement, if space is only an emergent network, if photons experience no length, if spin networks are the grains of space, and if microscopic wormholes lie beneath every entangled pair, then the natural next question arises: what are we in that gigantic quantum network? We can no longer pretend we're standing outside the universe like observers holding rulers, because everything we once thought was out there, from the Andromeda galaxy to the proton in the palm of your hand, is just nodes and links in an infinitely larger quantum graph. And so are we. Humans, thoughts, emotions, memories, bodies, minds, all are special configurations of quantum fields, temporarily stabilized by how entanglement is distributed across different scales. We are subnetworks of a larger network. We don't sit on space. We sit inside the network that creates space. The distinction between me and not me only makes sense at macroscopic scales. At microscopic scales, that boundary doesn't exist. The electrons in your brain are entangled with the photons hitting your skin, with the air molecules you breathe, with dust particles originating from stars that died billions of years ago. From a quantum perspective, the idea that I am a separate entity no longer holds firm. It is an emergent illusion, just like distance. Not a mistaken illusion, but a useful one. Like temperature helps us avoid tracking every molecule. When we say there is me and there is a distant galaxy, we're describing the world at low enough resolution to see a smooth picture that hides the chaotic structure underneath. Just as distance characterizes the average relationship of countless nodes in spin networks, our identity characterizes the average stability of trillions upon trillions of oscillating quantum states in our bodies. Indeed, if distance isn't fundamental, neither is separation. Two people standing next to each other aren't closer than two people 1,000 miles apart in the quantum sense. We aren't connected by space. We are connected by information, by entanglement. The degree of entanglement between two parts of a system determines their distance in emergent geometry, and that applies to every object, including humans. You aren't here while a galaxy is there. You and the galaxy are two regions of the same vast quantum network, described differently only because your scale blurs the deep connections. At the Planck scale, you're no longer located anywhere. You're a state in a graph. At the photon scale, you have no length. You're a point in a process. At the entanglement scale, you have no distance. You're a node in an information network. And when we zoom out to human scale, we see a stable shape with boundaries and positions. But that's just how the human brain tells the story to make it easier to understand. You don't stand outside the universe to observe. You are inside it. You are part of the equation. And when we view everything through this new lens emergent space, entanglement building geometry, spin networks as foundation, distance as statistical byproduct, that statement becomes not just philosophical but precise physics. We cannot ask, where do I exist in space? We must ask, how is the entanglement system that makes me positioned within the quantum network? Space only appears after that network becomes complex enough to emerge into smooth geometry. You don't live in the universe like someone standing on a stage. You live as part of the structure that makes the stage exist. If distance is an illusion, then isolation is an illusion too. When you look up at the sky and see light from stars that died millions of years ago, you're not looking outward. You're looking at another part of the network you yourself belong to. The truth isn't that we stand separate from a vast universe. The truth is there is no separation at all. Every electron, photon, spin, node belongs to the same structure, and you are just a stable pattern within that structure. Like a whirlpool is a stable pattern in a river. You cannot lift a whirlpool out of the river. Likewise, you cannot lift you out of the quantum network. Your body doesn't reside in the universe. It is part of the quantum connectivity that weaves the universe. This isn't mystical. It's simply accepting that your identity, the sense of a separate I, emerges from trillions of quantum states and temporarily stable entanglement relations. Like distance, identity is a macroscopic property, not a foundational one. In the deepest picture, there is no me in universe. There is a network, and there are patterns maintained for a while, then transformed, then dissolved. But the network remains. So who are we in the quantum network? We are a stable configuration of entanglement, a temporary pattern that quantum information chooses to express. When you understand this, distance, isolation, separation, all dissolve. We aren't lost in a vast universe. We are woven into it from the very first thread. From everything we've traced throughout this journey, from Einstein's relativity to entanglement, from holography to ER equals EPR, from spin networks to the Planck length, one truth stands out as clear as daylight. Distance has never been the foundation of the universe. It isn't something the universe gives us. It's something the human mind constructs to describe a reality infinitely more complex. At the deepest level, there is no how far, no where, no between 2 points. There is quantum information. There is entanglement. There is the structure of nodes and links in spin networks. There are non-classical correlations the human eye has never seen, yet they form the skeleton of everything we call space. Yet at the layer where we live, the layer of creatures a few feet tall, moving 1 billion times slower than light, with senses optimized to spot falling apples rather than microscopic wormholes. What emerges from that quantum layer looks like distance. We only see the smooth, average, low-resolution version of quantum reality. That version looks stable enough for us to use rulers and maps, stable enough to drive to the store, stable enough to look up at the sky and say, that star is very far away. But it's not stable enough if we want to know how the universe really works. Distance isn't fundamental because it depends on your speed. Distance is emergent because it arises from entanglement. Distance is observer-dependent because each reference frame has different values. Distance is quantum constructed because space-time geometry is encoded in quantum information structure. Even distance isn't continuous. Below the Planck length, how far becomes meaningless. Not hard to answer. There is no answer because space doesn't exist at that resolution. This leads to one of physics' most beautiful paradoxes. The thing that seems simplest in the universe, distance, turns out to be the most complex illusion. Not a mistaken illusion, but a useful one. A story, a model, a map. When you say I'm 400 kilometers from the moon, that's only true in certain classical pictures, at low speeds, in near-flat geometry, in human context, in the frame of the photon reflected from the moon. That distance is zero. In the language of entanglement, it's an event in an information network. In spin networks, it's the number of vibrating nodes connecting two regions. In general relativity, it's the geodesic length, depending on space-time curvature. 4 completely different descriptions, all correct in their own way, and none is the truest. That makes you realize physics doesn't chase absolute truth. Physics chases truth that's correct in context. There is no absolute distance, only different ways to tell the story of interactions between parts of the universe. And each way has value only when you ask the right kind of question. If we lived near the speed of light, we'd see space contract and the universe shrink. If we lived at the Planck scale, we'd see space melt into a quantum lattice. If we lived as photons, we'd see no space. If we lived as entanglement, we'd see no distinction between near or far. Yet from our perspective, distance is still beautiful. It makes the universe more poetic, vaster, more awe-inspiring. It turns the night sky into the most evocative thing human eyes have ever seen. It gives us the feeling of gazing into an endless garden of stars, while in reality we're looking at a quantum network where everything connects in ways Euclidean maps can never tell. Distance is the story we tell ourselves to live in a universe our brains cannot grasp directly. An extremely good story, good enough that we can build rockets, satellites, GPS, particle accelerators, and even bedroom walls. But when we try to step into the deeper layer, we have to set that story aside. Not because it's wrong, but because it's only story mode, not developer mode of the universe. And that's what's most beautiful about physics. It doesn't destroy our intuition to replace it with another intuition. It destroys our intuition to replace it with curiosity. You cannot feel entanglement, wormholes, spin networks, or the Planck length, but you can ask questions. And that curiosity, not distance, is what brings you closest to the universe. Don't worry about how far the universe is. Distance is just something you made up so you wouldn't be overwhelmed by quantum reality. Curiosity is the only measure that's always accurate, and you absolutely don't need to know how far you are to start asking questions. When you understand that distance is emergent, an illusion, a product of entanglement, you don't see the universe as smaller or larger. You see it as deeper, and that's the greatest gift physics has ever given humanity. Not making the world easier to understand, but making it more mysterious, more precise, more open. A universe that's not far, not near, but soaked into every part of you. A universe that's not a place you look into, but a network you belong to. We don't stand outside the universe to observe. We are part of the equation. And that equation is far more beautiful when we dare to look through distance to see its true structure. A universe that doesn't stretch out but connects. Doesn't separate but interweaves. Isn't distant but right there in every quantum. If you enjoyed this journey exploring the universe through a new lens, please hit subscribe so you don't miss the next adventures. See you in the next episode, where we continue peeling back the layers of reality and laughing with the universe in true Feynman spirit.